on boundary value problems and the shooting method. Okay, so I think this question is from page 92. So what's the difference between initial value problem and boundary value problem? So initial value problem is about the variables initially, which usually means that like time equal to 0, but also could be interpreted at just some value of x equal to 0, kind of dy dx. So that's what initial value problem is. Information is given about the solution at a single point. So for example, you have and it has to use an example to illustrate your answer. Well, you could possibly get by with one, the second example, I think. So this is a spring. So mass times acceleration is the spring force, and information is given about the displacement and the velocity at a single time 0. Okay. Whereas for boundary value problem, information is given about solution at multiple points. So for example, the bending moment is minus low per unit length. You're told about the solution at the start of the beam and the end of the beam. Similar stories would be the temperature of a steady state temperature of a rod, steady state temperature of a plate, where you know about the temperature at, in fact, a lot more than 2 points, but kind of infinitely many. Right. This next question isn't so much an exam question as kind of an exercise. So now what's very important is writing these things as 2 first orders. Now, will we have a little bit more of this in later videos? We actually won't. So hopefully you kind of figure this out, but the first step always is let the first derivative be a variable. So here, let the first derivative of temperature be v. And from here, what you do is you differentiate both sides with respect to x. If you differentiate the first derivative, you get the second derivative. And if you differentiate v, you get dv dx. And then what you can do is you can write your equation in terms of v and dv dx. So here I had the second derivative, which is equal to dv dx according to this. So I rewrite this original differential equation with dv dx. So replace the second derivative with dv dx, and then it's simply an algebra problem then to find dv dx on its own. And so you present your 2 initial value problems. Derivative temperature is v, we introduce that, and then essentially the derivative of the derivative dv dx we found here by taking away 0.210 minus t from both sides. Okay, so the initial temperature we know is given to us, but this is a boundary value problem. So what you have is you have information about the solution at 2 different points, x equal to 0 and x equal to 8, and that means that you don't actually know the initial v. The initial v is unknown. So a reasonable guess, like look, let's see where we're going. At x equal to 0, the temperature is 50, so that looks like that. X equal to 8, temperature is 100, so this looks like that. So a reasonable thing is to shoot straight at it. So do rise over run 50 over 8, which I'm guessing must be 6.25. You don't have to do that, but it just makes sense as such. Okay. But actually here it actually gave us the shot. So if you chose an initial slope of 10 just as a random value, you actually end up I'm not sure what step size that would be, that you're trying to hit 100 and you get 121.2. That's an overshot. Reduce the slope down to 0 and you get an undershot under 100, and then it's given your first slope and your first shot, your second slope and your second shot. You can use the formula, and the important thing is the formula. This is what you're trying to hit, which is the 100. So that's all this question asks for here. So that's the use of it there. Okay, this question is similar. Again, write it as 2 first orders. Let the first derivative be a variable v. Differentiate both sides with respect to x. So the derivative of the first derivative be the second derivative v with respect to x, dv dx. And now you can replace this with dv dx using the circle thing down below. So you get dv dx is minus 10 e to the minus 10x squared. And then as before, we knew the initial value of m that's given to us, but it's a boundary value problem, so we don't know the value of v at 0. Instead, we know the value of m at some other point, some second point. So v of 0 is unknown. And then again, it gave us the 2 shots. Now the 0 here makes sense. So at x equals 0, the moment is 0. and at x equals 6, the moment is 0 as well. So shooting straight at it would correspond to a slope of 0. So that was a reasonable first guess here. Okay. That gave it, you're trying to hit 0, that gave an undershot, and then increasing the slope to 10 gave an overshot, and then use this formula, and again, you're trying to hit 0, so that's your y of xf. Okay. Now an exam question. Now just note it says approximate t dash to 0. It's not looking for, like we have a step size of 1.5, maybe we'll add something here. Yeah. So we'll just look at the problem for a second. So suppose temperature at a point, distance x along a rod of length 6. So here's the rod going from a length of, well, 0 along the rod to a full length along the rod. And what we're interested in is step size of 1.5. So, you know, you go from 0 to 1.5 to 3 to 4.5 to 6. And we can call these temperatures at 1.5, temperature 1, at distance 3, temperature 2, at distance 4.5, temperature 3. And we're actually not being asked in this question to approximate these. We're asked to find the initial slope. So in any case, you have to write this as 2 first order. Like what? Okay, so we have to use Euler's shooting point method. I think just Euler's shooting method. We need to write as 2 first order. So again, introduce a variable v to be the first derivative, differentiate both sides, and then if you've done that, look at your second derivative as dv dx, replace your second derivative there in terms of dv dx, and off you go. Take away this from both sides and you're nearly there. So this is one of our differential equations, and this is a differential equation for t, so it takes the initial value of t. So this is differential equation for t, so this takes the initial value of t. And then the initial value v, as we said before, you don't know. Now, I've got a picture here of what's going on. We've got temperature versus distance, x equals 0, y equals 5. That's there. Distance equals 6. I might have said temperature equals 0. It's distance equals 0, temperature is 5. Distance equals 6, temperature is 65. So if we do a rise over the run, the rise in temperature is 5 to 65 is 60, the run is 6. So if you were to shoot straight at it, you get a slope of 10. So this is where we're going to try this and see how we get on. So we essentially, Euler's method is going to go from here to here, then here to here, then here to here, then here to here. And we're trying to hit 65, but we only guess, so we'll probably get overshots and undershots or you know, whatever. So I think one thing that people are having a bit of issue with, to look at the temperature here, you don't do an Euler method to get to there, you jump off here. So the first thing when you use Euler's method is it's not going to be an approximation of the temperature at 0, it's going to be approximation of the temperature at x equals 1.5. So I've kind of put that here. So the first time you use the Euler method, like at t equals 0, or excuse me, at x equals 0, the temperature is 5. There's no Euler method involved there. Okay, so we do previous, and maybe we'll look at the 2 previous at once. So the previous temperature is 5, because we're going like that. And then the previous v, well, we guessed the initial v to be 10. Step size in both cases 1.5, and then times previous slope. The slope of temperature is v, so we put in previous v, and the slope of v is dv dx, and its previous slope, so we put in the previous temperature. So this temperature here, we put in the previous temperature here. Hopefully I can get rid of all them easily enough. Okay, and so we have what's going on at 1.5. Now we go again. So again, the previous now temperature at x equals 3 was 20, and the previous v was 7.75. Just look a few lines up. Step sizes are the same. Slope of t is v, so we use previous v. And then if you look at dv dx, it's up the top of the page, and we put in the previous temperature, which was 20 for us. That's what's going on at x equals 3. We go to x equals 4.5. So again, we had this 31.65, so that was the previous temperature. 5.95 was the previous v, and then that 5.95 also comes into the slope, and the previous temperature also comes into the slope of v. And then finally we have one more thing to do. There's no point finding v4, it doesn't come into it. So previous plus step size plus previous slope, and the slope of temperature we found here is V. So that's where that previous V came in. Okay, and we got 47.298, and we're trying to hit 65,000 overshot. So we picked, sorry, that's an undershot. We're trying to hit 65, and we only got 47.3. So we try a bigger slope of 20, repeat the same thing again, back from the very start, and we get an overshot of 110. And now we come in and do our formula. So our first slope was 10. What we're trying to hit was 65. YA was our first shot, that was the undershot, that's there and there. YB was our second shot, that's the 110, that's there. And then the second slope minus the first slope, and we get 12.823. And in terms of the question that was asked, that's us done. But you can check your answer. So, like, why is that the answer? Well, remember that V is nothing but the derivative of temperature. In other words, it's T dashed of 0. So T dashed of 0, or sorry, it's T dashed. It's T dashed, say, of X. So if you sub in distance into 0 into these, you'll get T dashed of 0 is the same as V of 0, which is what we just calculated. Okay, now you can check your answer, because if you run with this slope of 12.823, you should hit that 65. And if you run it, so this is all using initial slope of 12.823, you find to whatever 4 significant figures, you do hit 65. So that kind of tells you that you've gone well. Okay. Right, another question, quite similar. I guess the difference is there were fewer points on the rod because the rod had a length of 3. And with a step size of 1, there was only 2 internal points, which made this a bit friendlier. So again, you write as 2 first order differential equations, which I didn't quite do carefully. And then we chose to shoot straight at it. It's going from 0 to 45 over a distance of 3. So the rise over the run, 45 over 3 is 15. So that's why I tried 15. And that is here. And oh yeah, I should have done the derivative. So they're here. Do them carefully. They're very important. If you don't do them, you're heading for a 0 on this, to be honest with you. And so we're trying to hit 45, and we ended up hitting 43.95. So that tells us actually that VA is going to be close to 15. So we just, that's an undershot. Go up to 20, it doesn't matter. You try 16, doesn't matter. We tried it with 20, and we ended up with 59. We're trying to hit 45, so that's an overshot. So you have an undershot and an overshot. Doesn't matter if you have 2 unders, 2 overs. Again, here's the formula. Here was the first slope and our first shot. Second slope, second shot. Y of XF, what we're actually trying to hit, and out comes 15.349. And this time, it did want us to approximate T at 1 and T at 2. So you do have to take this final and third shot. And we did that. It's pretty quickly. You get it here. So that's what's happening at x equal to 1. And this is what's happening at x equal to 2. You don't even need V2. Now you can check your answer, because you should get close to 45. And in fact, that gets you close to 45, 5 significant figures. And it seems that's all of those.